Okay.
I think we close the
Good
joke section
evening.
by now.
Yeah. Good evening, everyone, and welcome to today's Gifted World Masterclass. I'm Siddharth. I am one of the community organizers at Gifted World, and I'm very excited to see all of you here. It's almost becoming a year that we've been active, and I'm very excited to see a lot of familiar faces here as well. Many of you have joined our masterclasses and courses over the course of the past year, and it's really been a lot of fun. So first, I'd like to share a little bit Gifted World. We are an online community uh, where our goal is to help students who are talented reach their full potential. We work with students, we work with parents, we work with educators as well. And we have a really lovely group of mentors from all over the country and abroad who have conducted sessions for us. We have different kinds of offerings that happen at Gifted World. What you're in here today is a free masterclass. We have about 2 or 3 every month about varied topics. We also have some paid workshops that happen on on skill building and interactive topics. And we have one coming up in February on making bad arguments that's being taught by a computer scientist. So you can see you can probably guess where that's going to go. We also have upcoming masterclasses on the art of algebra and how to talk to a computer. We also, this winter, we are offering a series of courses, 5 session courses, where the topic is connecting the dots. So building conceptual learning in science, mathematics, physics, uh, generative AI, and other topics. Each of these courses are like graded for different levels, junior and senior. You can see all of the details on our website. So please do join in. Membership is completely free for everyone at Gifted World, and it always will be. And do check out also on our blog. We have a challenge that came up, which we're actually going to extend the time a bit, which has to do with uh, figuring out how does an electric car actually work, charging, discharging, braking, and fun stuff like that. So do check out Gifted World. And in case you want to know about past masterclasses, you can always visit our YouTube channel, which is on Gifted World. Just search for Gifted World on YouTube, and you'll see recordings of all our past masterclasses. So with that, I'd like to welcome you to today's session on why is gravity so special. I'm going to start off by introducing our facilitator for today, Sukanya. So Sukanya is a really experienced educator. She has a PhD in astrophysics from the University of Maryland and has been teaching and developing like curiosity in science for many decades now. She's a really fun person to work with and learn from. And I'm very excited for today's session. So with that, over to Sukanya.
Okay, thank you so much, Siddharth. And so it's really nice to see so many young people out here. And so let's start. And I hope I'm a bit technology challenged. So let's hope that.
Shall I just share the video?
No, it's okay. Yeah, you can do that. Let me just give an introduction before that. So
Yeah, sure.
I'll just come to this slide.
Yeah.
So can everybody see the slide? And I'll try the slideshow from the beginning. Yeah, I can even see people. Great. Okay. So the title of the masterclass is Why is Gravity Still So Special? And by the end, I want to convince you that among all the forces, there's something really unique about gravity, which none of the other forces possess. And it's a very intriguing, non-intuitive thing. And this is the force that is most familiar to us. And yet there is a lot to be learned about it. So that's what I want to talk about. So the first thing we're going to start by watching a video, and I'm sure many of you have watched this on YouTube. It's a really exciting one. But and you have watched it, you might have watched it before. I myself have watched it, I think, like 100 times. But every time I watch it, I'm excited about it. So we'll start out with that. So, so Siddharth, would you want to share, or
Yeah,
should I
sure.
try?
I'll do that.
Okay. So it's like a 3-minute video. So we'll watch it first.
Okay, just a minute. I need to change one thing about my mic. Uh, Are you all able to hear the audio?
Yes.
Cool.
This is NASA's space power facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions.
Is it on yet?
It's on. Are you not
I
able
can't
to?
see it. I can't see it.
Oh, wait.
Okay.
Visible.
Have the children, are the children being
Okay,
able
wait.
to
I'm
see
just
it?
doing it this way. Hold on.
Okay, let's
Okay.
try mine.
Conditions of
Let's
outer
try mine.
space. And
Okay.
it does that by pumping out the
Are
Okay,
you
can
able
you see
to
this
get it now?
picture?
I can see it.
No, you can see it, but I can't see it.
Oh.
I
Are
think
we
all
doing
of
it
us can see it. Yeah, all of us can see it.
Okay,
Sukanya,
I
I
can't
think
see
it's
it.
because your screen share is going on.
Okay,
Wait, hold on.
I'll stop my
No,
screen.
no, it's fine. It's fine. I am just taking control of the screen share. No issues.
Okay,
There.
correct.
Okay.
Yeah.
That's good.
So I've stopped my sharing.
Yeah. Are you all able to see it?
Yeah, now I want to.
This is NASA's space power facility near Cleveland, Ohio, and it
Can
is
you
the
put
world's
the closed
biggest
captioning?
vacuum chamber.
You want the subtitles? Yes.
Subtitles, yeah.
It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exactly. They came down exactly the same. Wow.
Look.
Watch right there. Look at how they hit right there.
Exactly.
You're back on the side. A little bit
Exactly
closer.
the same.
Feathers don't move, nothing.
Look at that. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this. The reason the bowling ball and the feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing that the ball and the feathers were being accelerated towards the Earth. So he concluded they weren't.
Okay. So I think we can stop here, right?
Yes, back
All
to you.
right. Okay, great. So, so you saw the ball and feather fell together, right? It's awesome. And how many of you had seen this before?
I hadn't
Okay.
seen the full video, but I have seen a small clip of it.
Small bit of it.
Yes.
So the thing is, and somebody asked in between, like, well, how is he breathing in vacuum? And you realize by yourself that the vacuum hadn't started yet. That's why there was nobody in the room, because nobody could have been there. They did it at through a remote control. Now, the thing is that one question I want to ask you, so we'll talk about that Einstein part later at the very fag end, but before that, we'll talk a lot about Newton. But let me ask you a question that imagine, you have these, whatever, the GoPro cameras that you put on a moving object and they record the video as they move along. So if I put a video camera, if they had put a video camera on the bowling ball and they were recording the feather, what would they see finally when they ran the video? What do you think they will see? Who raised their hands? You can, yeah, Anushka?
Ma'am, I think that the bowling ball would see the feathers staying still because both of them are moving at the same pace and the background moving upward.
Exactly. So when they would be taking a video, but what they will see is essentially a still picture. So they say, what's wrong with this? I took a video, but it's a still picture. So because they're falling exactly together. So there's no way, from the point of view of the bowling ball, the feather is standing still, right? Okay, so we'll talk more about that. So so the point is that, and this experiment could be done only because of the high technology of this removing the air, because you really wanted to see what they wanted to see is what happens when only the force of gravity is there. Because normally, has anybody out here seen a bowling ball and a feather fall together to the ground? Do you think anybody would be seeing like that? No, right? You always see so in normal, regular life, it's impossible to see this. It's because it's impossible to remove the air resistance, remove an extra force. So you want to see what happens only when gravity is acting. And in NASA, they had this fantastic vacuum facility, and that's how they managed to produce this. And it's just, that's a very good question. Why didn't atmospheric pressure make the vacuum chamber collapse? And that they have to make sure that the walls are strong enough to withstand that pressure. And that's a very good, relevant question, because the outside pressure would be much more than the inside pressure is almost zero. So the walls have to be, so therein also lies a certain feature of technology. Okay, so I'll go back to sharing. And okay, no, PowerPoint share. Yeah, here we go. So this is, so we've watched the video and we saw the ball and feather fall together. And now we're going to backtrack a little bit. Okay, now this is what happens with our...
You just click anywhere on the white part of the screen.
Click anywhere on the white part of the screen.
Or just press the down arrow.
Here we go. Yeah. So the next thing we do, we go back, like this is very recent and it went viral on the internet, and we take a peek into history. And almost 2000 years ago, there's 384, more than 2000 years ago. Yeah, somebody raised their hand. Viraj, do you want to say something? So maybe you say it. Yeah.
Sir, I raised my hand because I wanted to say something regarding this.
Yeah.
Ma'am, Aristotle had said this statement because that time nobody knew that there was also atmospheric pressure and air contributing to heavier objects so that they would fall faster. And only gravity will make everything fall at the same speed.
Right. So they didn't, Aristotle didn't even know, like the people didn't even have the concept of gravity, but there was the concept of observation. And Aristotle was a person who believed in observation, but did not believe in experiment. The concept of experimenting, trying something out actually was just not there. Aristotle believed that you could arrive at conclusions by pure thought and observation. And that is, and sometimes not even very accurate observations, because apparently, I don't know the truth of this, Aristotle believed that women have fewer teeth than men. And so the joke is that, why didn't Mr. Aristotle ask Mrs. Aristotle to open her mouth? So, but it's very significant that the concept of experimentation was not there at Aristotle's time. So he believed, like most of us would be believing, that heavier, because that's what you see, heavier objects fall faster than lighter objects. And that belief persisted for 2000 years, because Aristotle was a very great thinker and his influence on the world of science was very great. So nobody even thought of questioning it until, this is like the 16th century, almost the end of the 16th century. People started questioning this and wondering about it. Can you see the whole slide? This panel is interrupting my vision.
We can see the whole slide.
Okay. So I'll put it below. Yeah. So what this guy called Simon Steven is a Dutch, Flemish scientist actually. So he decided he had doubts about this, and he felt that, if one could, and he also had this idea that air resistance is the thing that's preventing us from seeing it. And he had the belief that maybe all objects fell at the same time, with the same acceleration, when the same rate of speeding up. So what he did, he took this place in the town of Delft called the Nieuwe Kerk, and he dropped two lead balls, one 10 times heavier than the other. And he had a wooden platform below, and the experiment was very crude. But what he concluded, that he heard the sound of both the balls falling exactly at the same time. And I think he had also observers on the bottom seeing the things falling at the same time. So this led to the belief that maybe, Aristotle was not right. And somehow or the other, gravity was not very well known, but whatever this thing is that making it fall has the property that it doesn't care about the weight of the objects. All objects irrespective of their weights, are falling with the same acceleration, and they're falling taking the same time to fall. Just a few years after this guy, Delft, and there was Steven, and there was another collaborator of his called de Groot. Two of them together did this experiment, apparently. And before that, also, people were starting to doubt Aristotle's conclusion. And then came along Galileo Galilei, the person who was mentioned also in the video. And Galileo really turned around modern science. He's really the father of modern science, in the sense that Aristotelian thinking was pure thought, pure logic, and you could get to the conclusions. And as I said, the concept of experiment was just simply not there. The Greeks were observing the planets, making observations, but if you have a hypothesis and you want to test it out, that concept was simply not there. And that was something that Galileo introduced full force. And here again is a myth, that what Galileo did was he dropped two balls, balls of different sizes. And he was born in Pisa, in Italy. And you all know about the Leaning Tower of Pisa. And apparently he dropped balls from the Leaning Tower of Pisa of different masses. And he found that they reached the ground at exactly the same time. And this, people say that this is also a made-up story, but it may not be exactly true. It just sounds nice and interesting. But Galileo did know about this, and if not actually dropping the balls, he did thought experiments and shorter ranged experiments, which made his belief that two falling objects did not care about mass. The acceleration was the same, and if you drop them with the same at the same time, they would reach the ground at the same time. You know, no matter like the difference in it, it didn't matter how heavy they were. And he was very convinced of that idea. He was very convinced of that idea, and he wrote about it. And another big thing about Galileo is that before that, he also wanted science to reach everybody. So before that, scientific texts were written only in Latin, and he started writing in Italian so that any common man could also understand science and think about it. And I'm not even talking about his telescope work and finding moons of Jupiter and craters on the moon, where he actually did experiments and showed that Aristotle was wrong in many of his ideas. So that was, 2000 years from Aristotle, and people started moving away from it and also doing experiments. Not to discount that Aristotle was a great thinker and he led the way on many things, but like as science progresses, new ideas are replaced by the old, replacing the old. So here it is. This is the old idea where the lighter one will be staying up and the heavier one will be falling, but they're coming together. And this, of course, Galileo or this other guy had no way of removing air. So they had to work with the air resistance. And that's why I guess you don't drop a ball or a feather, but you drop heavy lead balls where the air resistance is sort of ignorable, more or less. Yeah. Okay. So then comes this very nice video, which now time has progressed more, and though you're not making a vacuum, these guys in Apollo 15 on the moon, there is very little air resistance. They don't have to worry about air resistance. So let's see if this works.
Jim, we copied a both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here and hopefully they'll hit the ground at the same time. How about that?
There you go. So
How about that?
Mr. Galileo was correct in his findings.
So there, the two of them are dropped together, and on the moon they managed to minimize the air resistance. So there, and they saw the feather and the hammer experiment was done a long time ago. Okay, now this is your challenge. That if you're given now, you don't have that home, you don't have the capacity to make high vacuum or go to the moon, any of that. Let's just try it like at home. So if you're given an A4 sheet of paper and a heavy book of roughly the same size, and can you do this experiment to check whether they fall to the floor at the same time when dropped together? So I'm going to just stop this for a while and do the share again. So I want your opinion. Can you think of a way that you have a paper and a book thin piece of paper. So it's very light, right? The paper is definitely lighter. Okay, she's dropping it. So did they fall together, Akshara? Did they fall together? I saw you dropping it.
As
The book falls first.
the small book fell first because there was more air resistance here as compared to the moon or the vacuum tube.
Exactly. But can you arrange things so that both of them fall together? Can you think of a way to do it so that you don't need high vacuum? You don't need, like you don't need to go to the moon because the book is heavy. So, but now Galileo showed that heavy does not matter, right?
I think we can.
So Viraj says, let's go to a room and remove air. No, I'm not going to let you remove air. It's not easy to remove air. Think of something else.
We can cover it with a glass ball.
Glass ball is going to break if you drop it, no? Okay.
No, we can cover the objects with
cover
a
the
big
object
glass
with a glass ball.
Ma'am, how about like, for example, we can take like, instead of the book and the paper, we can take one hollow plastic ball about the same size, and the other one would be the lead ball. So the lead ball is heavier than the plastic ball, which is hollow, but then is the same size. So when you drop it, both of them should come first, maybe like.
Yeah, that's fine. I mean, I agree. That's a good experiment. But I insist on just the paper and the book.
Ma'am.
I'm not going to let you get glass balls or hollow plastic balls or whatever.
Ma'am,
if
we just crumble up the paper,
yes,
we can just crumble up the paper and throw and leave it at the same time as the book. It will drop at the same.
Right. So that's a good solution. That like you can crumple up the paper and drop it together, and that's going to reduce the air resistance. We can fold the paper. We go to the moon. No, go to the moon is not a solution, acceptable solution. Okay.
Ma'am.
Yeah.
Can I share like why the book drops faster than the paper?
Yeah.
So basically, to get the amount of newtons on an object, which is the pull of gravity on it, we have to multiply the number of kilograms by 10. So let's say the paper is 0.1, so that would make it having a pull of only 10 newtons. But then if the book will obviously be heavy, it might even be 1 kg. So it will have 100 newtons of pull on it, so it will get pulled down faster.
No, but the pull doesn't matter. We just saw that, like the heavy object and the light object fell together. And there is no doubt that, the weight of the feather is less than if you do whatever you multiply it by G and
we
whatever.
So here we must reduce the air resistance.
That's the key thing. So who was that? Who said that, the one
Zuhair. Zuhair.
Crumpling, no? Who gave the crumpling solution? Anaga?
Crumpling came from Anaga.
Okay. Crumpling solution is a good solution because you'll find you can try it out at home. Crumpling will reduce the air resistance, and it will make it at least maybe not exactly the same time, but about the same time. And I will give you, so I want you to think a little deep, harder and not even crumple the paper, yet get it to fall at the same time.
Ma'am, we have to, ma'am,
I tried by doing them both vertically, like.
Both vertically, okay.
Do we cut the paper short?
Yeah, almost at the same place.
Somebody, so let me, I mean, I can keep you thinking, but let me give my solution. So what my solution is, roll the paper, drop paper first is not good enough. You have to drop them together, they will reach the thing. I will turn into a balloon if I do so, is it? So you drop paper, you have to drop them at the same time, like can't change the condition. So how about this? I don't have place to drop this. What I've done is I've placed, this is not quite A4, but I've placed the paper on top of the book and I drop them together. Are they going to fall together or not?
Oh wait, ma'am, I think I know what you're trying to say.
I don't think they might fall together, but there's a chance they won't if a piece of the paper is sticking.
Try it out. Try it out.
If the
Ma'am,
piece of
ma'am, I
paper
have
is
a solution
sticking
to that.
outwards, then it will not fall.
Air will come. Air will come minimally from the sides. You try this out.
Ma'am,
Yeah.
even if a small piece of the A4 paper is outside of the book, then like the air will just push the
It'll
paper.
be a little harder, but it's very doable. You have to try it out. All you have to do is this.
Ma'am, or a better way we can do it is just keep the paper inside the book.
Keep the paper inside the book. Okay.
Ma'am, there's another way. Can I say?
Yeah.
So ma'am, basically, like if you have like a paper and you just place it anywhere on your body and you run very fast, that paper will remain there. So if you take the book like you did, but instead of keeping the paper on top, you put it below, both of them will fall at the same time.
Below, I don't think so. Below will not work because the air resistance will be again operating on the paper. You play around with this, okay? You may disagree with me, but my idea is that if you put it on top, they will fall together.
Ma'am, it works because it works because as long as the paper is inside the boundaries of the book, the air will flow around the book.
It cuts out the air resistance completely. So actually, you are showing exactly that feather and ball experiment at home, much cheaper and much more easily. Okay. All right, Harini, this is the last question I'll take, and then we'll go back to like other stuff. Huh? And you can keep trying. Yeah. I know. Yeah, you have dropped it. Yes. Yeah.
One more
Okay, technically the paper would never reach the floor. That is an interesting point, like, I sort of agree with that. You can take a thin, heavy book, and there is a small discrepancy. I agree.
Ma'am, it's not about the paper reaching the floor, ma'am. If we keep it like this, they
Falling
travel the
together.
same amount of.
Yeah, whether they're falling together. That's the crucial thing. That's the crucial thing. Okay, all right. So, okay, you fold in the paper.
Like the paper was working. So like if I do this, they both fall at the same time.
They fall
like
at
if
the
I
same
keep
time,
it under, then it falls at the same time.
Under also is falling at the same time.
If I keep it under, the air would like just hit this part. So keeping it stuck to that.
Exactly. Okay, that's great. Wonderful. And you can throw you can try it like a million times at home. And okay, now what is a joke out here? Let's go back to this. Okay, let's go back to my slides. And that was great. You all had very good ideas. And all right, so I'll go back to my slide from current slide. Now, so Galileo did all this work, like amazing stuff. And by that time, more or less everybody was convinced that heavier objects and lighter objects all fall together at the same time. If they're released at the same time, they fall together. Okay, but then came Newton, and Newton was born the year Galileo died. And actually, Newton and I share the same birthday, but that's also a funny story because Newton was actually born on Christmas Day, 5th December, 1642, but his birthday is counted as 4th January, 1643, because the calendar changed from Gregorian to Julian or the other way around. So his birthday also changed. So what Newton did on the groundwork of Galileo, he made mathematical statements about this, where he could really show in terms of quantitatively that this is true, and he thought about motion, he thought about gravity, and he gave a law of how gravity, two bodies are attracted by, so now, and this happened at a very interesting time, and like we have all these new apple falling on the head story, and that's probably not even true. That's also a myth, but what happened is that a very interesting thing happened is that just like you people had to go through this big gap of being off school during COVID. You know, there was a pandemic, so all schools were closed and you had to sit at home. Newton similarly went to Cambridge, and at that time, there was this great plague, you know, bubonic plague, 1666, and Cambridge was closed. So he went back to his aunt's home at Woolstock, and there was a big apple orchard, and he used to like sit there thinking about physics, thinking about motion, thinking about gravity, and that's where he did his greatest discoveries, though they were published much later. So some of you, sixth standard, probably have not learned, but what Newton found out at that time, he was always, from the time of Greeks, people always worried about how people, why, why things move, how things, oops, these dogs, you know. So he found out, he gave three laws of motion. I'm stating two. One is that a body will remain at rest or move with uniform velocity unless a force acts on it. First part sounds kind of silly in the sense that, of course, if you don't push a body, it's going to be at rest. The fact that it can move with uniform velocity without a force is quite unusual. And then he also gave a law as to how the force, what is the result of, if it's moving or pushing it something with a force, is going to change its velocity. Changing velocity means creating acceleration, a change of, and he said that the force and the acceleration are related through this equation. F is equal to ma, where F is the force and m is the mass of a body, the amount of matter in a body, and times the acceleration. So, and mass, he also taught, this is sometimes also called the law of inertia. Inertia means like the reluctance to move or change your state. So the more mass it has, a body has, the more reluctant it will be to move. You know, so it is like a mass is a measure of inertia. That's what they call it.
Ma'am, what represents R in this equation?
Okay, now this is further down. Then he also found out, so this F could be any force, not necessarily gravity. And then
I know, but then what is R?
Yeah, R comes later. We have not even gotten to the, I'm just talking about the top box. Huh?
Okay.
So I will come to this. Oops. I cannot get rid of this panel, so I cannot see the thing. Further down. Yeah. We're going to lose it. So then you also found out, when this apple falling legend, this law of universal gravitation, and I've highlighted universal because the apple falling is just understanding that there is an attraction between the apple and the earth. But what Newton saw is that this is not just about the apple and the earth. This is about any two objects in the universe. You know, so if there are two objects with masses m1 and m2, they are going to be attracted to each other. And I'll tell you what r is. R is the distance between the two objects. So right now, whoever was asking me the question, though I am, you know, kilometers away from you and behind the screen and everything, according to Newton's law, there is a force of attraction between the two of us, and the way to calculate it is that there is this big constant g, and there is your mass and my mass and the distance between us, and that has to be squared. So this is the law of gravitation. Don't worry about the details too much. The only thing to understand is that it gets stronger if you have more mass. The attraction gets stronger, and also it gets weaker if you're farther apart. Yeah.
So this equation, what's the purpose of it? Is it meant to measure how much inertia one object has, or?
No, this equation is meant to measure the force of attraction between two objects which have mass. Okay. So any two objects in the universe, the Earth, sun, moon, apple, Earth, you know, like orange, ping pong ball, whatever, you know, any two objects in the universe are attracted to each other according to this law. Like, so it's universal. Any two objects, any particle that has mass and any object in the universe, any physical particle always has mass. So, and it is always, they are attracted to any other object in the universe according to this law. So this is a specific force. This is a force of gravity. And up there, where it says F equal to ma, it could be any force. This works for any force, not necessarily gravity. Okay. And he also gave a specific form of gravity, for gravity. Now, okay, let's see. Now it turns out that scientists have figured out that in the entire nature, there are only 4 kinds of forces. They can be classified into only 4 kinds of forces. And our main hero is the gravitational force, which I just told you, that is the force between any two masses, and the electromagnetic force. And this gravitational force is long range. Long range means that even if you go away from each other, like very far apart, the force grows weaker but never goes away. There's always some attraction because it decreases. And then there is the electromagnetic force, which only acts on charged particles. Like if you have charges on the particles, static, you know what charges are, right? You must have studied some electricity in school. So when charged particles like electrons, protons, or if you even rub on a very dry day, you get these static shocks. So if you have charged particles, they are governed by a different force law, and that is electromagnetic force. The 2 other forces we don't have to know about so much. One is called the strong force and the other is called the weak force, very unimaginative names. The strong force is the force that holds a nucleus together, and a weak force is what causes radioactive decay of nuclei. Or don't worry about them. And they are very short range forces. They hold only within the nucleus, holding 2 protons together, holding a proton and neutron together. And that's within a very, very tiny they are not long range forces. So we're going to worry about only the gravitational force and the electromagnetic force, mainly the gravitational force. That's our focus, but I'm going to compare it somewhere along the way with the electromagnetic force. And I put electricity and magnetism together because people have found that these two are connected, and you can talk about a unified electromagnetic force. Now you might think that right now we were talking about taking away air resistance. Where does that fall into all these things? It doesn't look like any of these. But it turns out that air resistance, friction, all of these forces are actually, it can be understood as some kind of electromagnetic force. It's a little complicated, but they're not gravitational forces, but they're electromagnetic forces. But the interesting thing is that all of these forces, all particles are affected by gravity, whether they have charge on them or not, because anything that has mass is affected by the gravitational force. Okay. Now gravity, if I compare
sorry, there's one question from Inian.
Yeah.
Go ahead, Inian.
Yeah.
VN sir, so I read in a book that isn't it electrostatic force?
Electrostatic force is the force between the when charges are held still. Okay, so that is the electrostatic force, the forces between static charges.
And isn't also strong and weak nuclear forces?
Yeah, there are nuclear forces. So I listed the strong and weak nuclear forces, but we won't, I just did it for the listing purpose. We won't worry about them too much because they are only operating within, like the small region of the nucleus. We're going to talk about, and gravity is like much more, no matter how far away you go on, and if you have mass, you are subject to gravitational force. But I'm going to compare it with the electromagnetic force and actually the electrostatic force, in the sense that 2 static charges, when they're held together, held apart. So, but it turns out that gravity is much, much weaker than an electromagnetic force. So if you take 2 electrons And the electrons have both mass m and charge q, and you hold them apart the same distance, and you take the ratio of the electric force to the gravitational force. The electric force is bigger by a whopping factor of 10 to the power 42. You know what 10 to the power 42 is? 1 followed by 42 zeros. So it's huge, much, much stronger. So gravity compared to electromagnetism is a very weak force. But there are lots of similarities, and I'm going to so many, almost 100 years after Newton, there's this gentleman called Coulomb, and he came along and found out the force between two charges, like separated by a distance r. And look at it, look at the formula. It's very similar. And of course, charges are a little different from masses because they can attract as well as repel. Masses always attract. But the form of the forces are very similar. The form of the forces, there you had m1, m2 divided by r square. Here you have q1 times q2 divided by r square, where q1 is a charge of one particle, q2 is the charge of the other particle. In Newton's law, you had the mass of one particle times the mass of the other particle. So and divided by r square, exactly the same form with mass replaced by charge. Yeah. So there's a meme where there is Newton here and Mr. Bean is Coulomb, and he's copying from Newton and just writing down the same law with Q in place of M. So they look almost exactly the same, with charge replaced by mass replaced by charge. But even between two electrons or two charged particles, gravitational forces will be there because whatever has mass will have charge also. Okay. Now, this is little bit, so Coulomb's law, as I said, I'm putting a E subscript because that is the electric force. So that this K and G are different constants. So you have Q1 times Q2 divided by R square. This is the law. Newton's law tells you this is M1 times M2 divided by, and I'm putting a tiny subscript G to say that this mass is called, it appears in the law of gravity, so I'm going to call it the gravitational mass, and it's almost like a we can call it a gravitational charge because they look exactly the same, and if it's as if it's a new charge related to gravity. Mass is like gravitational charge. Okay, now I'm going to talk, and this is only a little bit of mathematics here. Remember, Newton's second law says force is equal to mass times acceleration. Now, and here I've noticed that I put a subscript I here, because this mass in principle need not be the same as that mass, because that appeared only in the gravitation law, and this appeared in this law, which doesn't even care about which force we are talking about. It will hold for, so I call it the inertial mass, because, so I put a little subscript I. So in principle, let's believe that those two need not be the same. Okay. So now let's look at, so the acceleration, if we turn out of any object, if I turn this equation around, will be F divided by Mi. So if I look at an acceleration of a charge Q in a uniform electric field E, what an electric field is really E is equal to electrical force divided by Q. That is what electric field is. And even the gravitational field here that I'll use is the gravitational force divided by mass. That's the definition of a gravitational field. So if I look at the acceleration, in which how the velocity is changing of a charge Q with a mass m in a uniform electric field E, it is given by Q over Mi times E, which is the constant electric field. Now, if I take a charge of different charges will accelerate with different values in a uniform electric field, because it will depend on the ratio of Q over Mi. Now, acceleration in a uniform gravitational field is going to depend on this ratio of gravitational mass divided by inertial mass. And that gravitational mass, remember, came from this law, like Newton's gravitational law. Now, next thing is that it's observed in nature that this gravitational mass is identical to the inertial mass. So mi is exactly equal to mg. And if I put that into this equation, if mi is exactly equal to mg, what does this ratio become? Mg divided by mi, how much will that be? If mg is equal to mi, can somebody tell me?
Ma'am, 1.
Yes, so this will become 1. If this becomes 1, then A will become G, right? Right, because this factor will become 1. So that is why in the gravitational field, all bodies move with the same acceleration. It just happens that this is just an accident of nature, or this is it's a fact of nature that these two quantities are equal, and this is called the equivalence principle. And this is very special about gravity. Notice that this does not happen in the electromagnetic field, because Q is not numerically equal to mi. So if the Q over mi, in general, it's not going to be 1. So particles of different charges are going to be moving with different accelerations in electric fields. Okay, so this is very special about gravity. So that's why all references to mass are removed here in the acceleration. So it's telling you that all bodies, irrespective, mass doesn't even appear here. So all bodies, whether they're heavy or light, they're all going to be moving with the same acceleration in a uniform gravitational field. And that's exactly what we saw in that feather and ball experiment. Because this one is lighter, this one is heavier, but the gravitational field does not care, the acceleration in the gravitational field does not care about mass. It's independent. The equivalence principle is telling you, no matter what, that mi equal to mg, so that factor became 1. So A is equal to G, everything is going to be falling with the same acceleration. So that's why they're falling together. They're just falling exactly together. Okay. Now, this carries over to many other consequences. This is falling directly down. It's also true that if you're projecting any object, this is like a cannonball or a ball or whatever you're projecting. Again, you're giving it a horizontal velocity, but the only force, ignore that, all of what I'm going to talk about now, ignoring the air resistance, because if you take in air resistance, everything gets messed up. I'm only talking about what happens in the pure gravitational field. So if under pure gravitational field, since the acceleration, it doesn't care about the mass, every object is going to take the same path and have the same range. So if you had a cannon and you shot out a watermelon or an elephant or a heavy cannonball, everything is going to land up in the same place at the end, hit the ground at the same time at the same distance. So that seems really weird, but that's what the equivalence principle is telling us. And that's essentially the same thing as, in some sense, it's the same thing as the ball and feather. Exactly the same thing, because it's telling you that gravity has no way of knowing the acceleration is the same. So if you're starting it out with the same velocity, initial velocity, it's going to hit the ground at the same time because the acceleration is the same. Okay. So this is the contrast with paths of charged particles in magnetic fields or electric fields. So if you have a positive charge, the particle is going to go like this. If you have a negative charge, the particle is going to bend in this way. If you have no charge, it's going to go straight. So it cares about what kind of charge it has. If you think about mass as gravitational charge, in a gravitational field, the trajectories do not care about what mass it has. They're just going to be the same if you started it out with the same velocity. So in that sense, gravity is very special indeed. And we never see this feature of gravity very explicitly because air resistance is always present. But if it was not there, this is what would happen. This also manifests in the sense that now you no longer see these kind of clocks because these are pendulum clocks, grandfather clocks as they call them. And these were used to keep time. And basically it's the period of a pendulum going back and forth, which has a definite value and it keeps time, and that's connected to the clock. And that was used a lot. And now they are sold in antique shops. But the interesting thing is that this pendulum bob is also for, Vijay, Vian, tell me.
Ma'am, someone else also had the same question. Why aren't the unlike charges attracting? You showed us the charged particles in a magnetic field, right?
Why aren't the like charges attracting?
Yeah, why aren't the unlike charges attracting?
Unlike no. Okay, let me go back to that picture.
Yeah.
Because I'm actually not putting them together. I'm just illustrating that if I put and this is about moving charges. Moving charges, magnetic fields only respond to moving charges, not to static charges. Okay, they bend the paths of moving charges. So I'm not, you're right, it's misleading because it looks like I'm putting them both together. I'm just illustrating that if I put a positive charge there, it will bend there. Next, take away the positive charge, I put a negative charge there, and of the same magnitude, but it's going to bend the other way. So that's why the magnetic field is actually distinguishing between the kind of charge you're putting. Whereas the gravitational field is not distinguishing the paths of the charges, different masses. And that's the illustration. So you're right. Thanks for pointing it out. It's not like I'm putting them together. If I had put them together, yes, they would attract. Yeah, I'm just saying that I'm putting, and these crosses represent a magnetic field. It could be like you're putting a big horseshoe magnet out there or an electromagnet, which I have not shown. It's just depicted by these crosses. Okay. Okay. Thanks for pointing that out.
Yes, ma'am.
Okay. So this is another place where, the period of a pendulum, it's actually independent of the mass. It doesn't. So pendulum bob is also falling under gravity, and it's taking the same time, irrespective of mass. So you have all these bobs. These are available on Amazon. And if you stick them on here, different material, different masses, you'll find that the time period, just like the ball and the feather that fell at the same time period is going to be same no matter what you put at the end of the pendulum, as long as you keep the length of the pendulum the same. Okay. Now, the thing is that scientists are not happy with, just establishing this has been seen many, many times, established to the fact that heavy and light bodies fall with all bodies fall with the same acceleration has been tested very well, but they're still not satisfied. So they have this space test called the microscope mission, which takes which is an orbiting satellite, and they take two hollow cylinders of different compositions, different masses. One is made of platinum, of titanium, and see how they fall, whether they fall with different accelerations or not. And they have verified this to the accuracy of precision of 10 to the minus 15. Like the thing is that they differ. If they differ, the ratio of that is only going to be 15 zeros after a decimal point. So that's like phenomenal. And they're still not happy. They have another mission going, which plans to push it to 10 to the minus 18. And the reason you push it is because if you see a violation, it's going to lead to new discoveries. You have to scrap all this old physics and find something new. So they keep pushing the limits and testing and verifying this equality to greater and greater accuracy. And that's quite awesome. Now, I'm going to talk a little bit about, so now if we saw that if something is falling, the two were falling and they didn't even know that, if the bowling ball looks at the feather, it feels that it's at rest. So now if you have an astronaut, which is almost with a spaceship with engines off in almost a gravity-free region. You cannot be in a gravity-free region completely, but far away from all planets. And somebody's raised the hand.
Ma'am, so I saw this one Boeing Starship where Usain Bolt was trying to run as fast as he could on Earth, but then it
Okay.
slowed him down. Why did that happen?
Okay, is that so? Okay, I'll have to
Yeah,
think
ma'am.
about
So
it. Okay, so let me complete this, and maybe if we have a little time in the end, we'll discuss that. I'll have to think about it. Yeah, I'll have to understand it better. So if you have, so you have this, man in this whatever spaceship, which is engines cut off out in space. So there's no gravity acting, right? No gravity acting. So that means there is no air resistance either. So no force on it. So Newton tells us that if he now takes a ball and releases it at rest, he holds a ball and releases it at rest. What is it going to do? What do you think it's going to do?
It is not
This
going to
fellow.
fall down.
No, it will fall.
What do you think it's going to do?
It will stay in the same position.
It will stay in the same position because there's no force acting on it. There's no gravity on it. I mean, it has no reason to move. If he releases it at with zero velocity, it's just going to stand there, stay there. That's what's going to do. And so that's very weird, but that's exactly what. Or if he releases it with slight velocity, it's going to continue with uniform velocity. It's not going to accelerate because there is no force on it. Okay. Now, this is exactly equivalent to on Earth if you were in an elevator and your elevator cable broke. But I mean, pray to God that that does not happen. But if it did, what is going to happen? It's going to fall. It's going to be in free fall, right? It's going to fall with 9.8 meters per second square acceleration. Everybody agree?
Yes.
Yeah.
Yes.
So this is exactly like, so he is like, so let's see that he is the bowling ball and he has a feather in his hand. So if he puts the feather now next to him and releases it, what is he going to see?
They're staying. It's there. It's already.
Stays in the air.
It will be there. That will
It
happen
will
with
be
all
there.
the objects.
So it will be just staying still. So this is exactly like what will happen if what the astronaut will see in like gravity-free space. So now he's actually on the Earth and in this cable-free braking elevator falling freely, and he's actually feeling, and this is like what they call weightlessness, and he'll be exactly doing because that's what the bowling ball and the feather were doing. They were just falling together under gravity. So he's also falling together, falling freely under gravity. And if he has the ball next to it and releases it, it's just going to stay there. So these two situations are exactly equivalent. And this is exactly what they also see in the International Space Station, or that's what astronauts see. If they put a ball out there, it's just going to stay there. So they're floating in there. So all these situations are actually equivalent, right? So free fall is actually equivalent to zero gravity. That's a very important thing to realize. And now the only confusing thing might be because this is the International Space Station, and the International Space Station is actually in orbit around the Earth, right? It's not exactly like the falling elevator. So you might feel that, oh no, it's not really falling towards the Earth. So how does it work? Why is it the same thing? But actually what happens is that even if something is falling, even if it's in orbit, really the gravitational force is only pulling towards the Earth. So the acceleration is really only in the along the Earth and satellite line. It just has a horizontal velocity or orbit velocity that keeps it going in circles. But it's actually really falling towards the Earth, but it's not allowed to fall because of its velocity. So the falling part is identical. So the ISS is continuously falling towards the Earth, and so is the Moon. So all the planets are also falling towards the sun in the same sense. So that's why this is happening. You are seeing the same thing on the International Space Station that you would see in a gravity-free environment, that you would see in a elevator with a cable cut. Okay. Now, the opposite also happens, that gravity can also be simulated by acceleration, the other way around. You know? So this man is standing in a, I don't know, elevator, a box on Earth, and, he's feeling his weight, like he's just, you're pressing on the ground is reacting back on you, so you're pushing back on you, so you're feeling your weight, you're standing there. This will be exactly equivalent to if in a spaceship, engines are on and it's accelerated upwards at 9.8 meters per second square. So you copy exactly the acceleration due to gravity, and out in space, you make it accelerate at exactly that, but upwards. So it's similar to, the push you feel when you're in a car and it starts moving and it accelerates and you're pushed back towards the seat. Yeah. So similarly, when it's accelerating upward, the astronaut is pushed towards the floor of the spaceship. And if he doesn't know that he's in space and being accelerated, he won't know the difference between the situation on the left and the right. So now what would he do on the in the elevator now? If he drops a ball, it's going to fall to the ground with a certain trajectory. If he drops a ball on the spaceship, it's going to fall to the ground in exactly the same trajectory as if there was gravity. But really, there is no gravity around there. You're just making a false gravity by creating this acceleration. So it works both ways. Free fall is equivalent to zero gravity. Gravity can be also mimicked by acceleration. Okay, say acceleration of a specific kind, acceleration exactly of the free fall acceleration. Now, this is what Einstein, the way we stated the equivalence principle was that the inertial mass has to be equal to the gravitational mass, or you say that all bodies are falling with exactly the same acceleration. The way Einstein said is that there is no experiment that can distinguish a uniform acceleration from a uniform gravitational field. They are exactly equivalent. And this is exactly what this picture is also saying, that if you are stuck inside this box and you're on the Earth and you're stuck inside this spaceship, and nobody told you that you're in a spaceship, but it's being accelerated exactly at 9.8 meters per second square upwards, you won't be able to tell that you're not on the Earth unless you're told, so there is no way of, so any experiment that you're conducting, that for dropping a ball, will work exactly the same way. So gravity somehow can be exactly mimicked by acceleration. And this is Einstein's statement of the equivalence principle. So Einstein had this hunch that if the trajectory is, like I saw, that whatever you throw, they're taking the same trajectory irrespective of the mass. And mass is the property of the object, right? But it doesn't, the trajectory doesn't seem to be depending on that property of the object. So if the trajectories do not, under the influence of gravity, do not depend on the properties of the object, perhaps gravitation is related to something else, something that all these objects share. And what do all these objects share? They share the space that they are traveling through. They share the time that they are taking to travel. So maybe gravitation is special in that it is related to the properties of space-time itself and not to the properties of the object. Okay? So here I'm getting a little ahead of myself, and you don't have to understand all this, but this is just, so the equivalence principle, as we talked about, was the starting point for Einstein gave a new theory of gravity, which looked at gravity not as a force, but as resulting from distortions of space-time. And you don't have to understand all of this. I'm just putting it out there. And in a very short, pictorial sense, if you have a very flat surface and there are two ants moving, they're moving with uniform velocity and they're moving parallel to each other. There's no force on them. So they're moving in a straight line, so this is how they will look. Now, these ants are living on a tennis ball, but they don't know that they're living on a tennis ball. And there's no force on them. They're just trying to go, since there's no force on them, they're just trying to go as straight as possible. And they're going as straight as possible, but because they're on a curved surface, their trajectories are curving. Somebody from outside will say that, there's a force on them, that's why they're coming together. So that's sort of Newton's point of view. And Einstein's point of view is that it's because the surface on which they're moving is curved, and that's why, and they are doing their best job of moving without force as straight as possible, and that's why this is happening. So that's roughly the idea. There's a lot of mathematics behind it. There is a lot of background and physics behind it, which it's not possible to talk about. You need some preparation to learn about it, but I'm just putting it out there as this is all following from the very special property of gravitation that all objects are falling with the same acceleration. It just started from there and it gave rise to a very new theory, and gravitation stands apart from the other forces because of this very special property. So that's a story for another day. So I think I'll stop here and then thank you very much. And I'm going to, let's see, I don't know what.
I can help moderate questions.
Yeah, I'm just going to stop here.
Okay. Yeah. So just before we get to the questions, I wanted to tell you that in case you enjoyed today's class, and we will definitely get to the questions, I want to share with you about Sukanya's upcoming course that is starting just 1 week from now. It's starting next Saturday. And it's called Connecting the Dots in Physics. It's for students in grades 6 through 8. And over December 21st to 30th, over 5 days, that's Saturday, Sunday, Thursday, Saturday, Sunday, you will have sessions like this, maybe I think a little bit more advanced also, discussing about building your conceptual knowledge in physics. So this is a course that I think Sukanya first offered way back during the pandemic. Yeah. And now we're back with several other connecting the dots as well. But Sukanya's is the first one starting off. And as I've shared details in the chat of a special discount that's available for the first 10 people who sign up from today's class. And so Sukanya, would you like to tell us a little bit about the course that's happening? And then we can
so the thing is that I'm sure like all of you are learning some physics in your regular school. So the question might be like, what is different here? So in a regular course, sometimes there is no time to delve into deeper aspects of the theory, think about, look at the history of ideas, because very often like you're told like this is the law and now you start calculating. But the conceptual connections are often not elaborated, and also like applications, interesting applications in various fields or connection with other fields, all of that is not put together. So what I would like to do is, even in things like understanding motion, understanding gravity, understanding floating, sinking, simple things like that, properties of matter, how to really literally connect the dots, in the sense that you might have seen glimpses of them here and there, but to see like a unified picture, how they're all connected, and delving into deeper aspects of it, and looking into interesting applications, looking into challenge questions, maybe thinking of designing experiments etc., etc. So, so that's basically it. Yeah.
Great. Thank you so much, Sukanya. So there are a couple of questions in the chat, and so I'm going to ask people to you've all raised your hands if you have questions. So I'm just going to ask you to unmute yourselves one at a time. So Akshara had a question about, wait, I'm trying to find that. Yeah, why can't electromagnetic force be weaker than gravity?
Oh, why can't it be weaker than gravity? I think we cannot ask those questions in the sense that our job is to describe nature, right? Because after all, what is science all about? Oh, string theory, no? I think I don't want to jump so far ahead. Explaining string theory with respect to gravity because it requires a lot of mathematical background, and I don't want to dilute the stuff. String theory is a model that well, let me get to Akshara's question first, in the sense that these are things that after all, unlike mathematics, physics is all about observations and experiments. If your whatever theory you've constructed, if it conflicts with experiment, that theory is no good. So basically, whatever theory you're constructing is really a systematic putting together of all the observations that you've seen. And in our observations, this is what nature has given us, that the electromagnetic forces are stronger than, and the thing is that the stronger and weaker is a very it's important to understand how you say stronger or weaker, because you have to know how to compare the thing. So the 10 to the 42 number that I gave was very specific. So you have to keep a lot of things constant. So I have two electrons which are interacting gravitationally as well as electromagnetically, and I've kept the distance between the same, right? Keeping the distance between the same, I'm comparing the two things. The objects are the same, they have charges as well as masses. Now, you cannot, and in certain cases, gravitational forces are very strong, right? All depends on what you're looking at. Because after all, gravitation is keeping our world together. I mean, the gravitational forces of the sun and the moon are huge. And because the masses are very big. Now, the point is that if in addition the sun and the moon were charged, the electromagnetic forces will completely overpower the gravitational forces. So it's just, we are lucky that they're not charged. So it's just I would say this is just an observational fact. So we don't have a deeper understanding of why. But it's a relevant question. It's a relevant question. You can always ask that why is there hierarchy of these forces? Why is one bigger than the other, and what determines that one is bigger than the other? And I don't think anybody has the answer to the question yet. Yeah, that's a good question though.
Okay. Akshara, did you have any follow-up?
What?
No, okay, cool. No issues. I wanted to know if you had anything else you wanted to ask. Anyone else with questions, please raise your hand. So Vrishan also had a question saying that if the masses are in two different mediums, water and sand, then will their motion change?
That definitely will change, because that's a good question, because if there are two different mediums, then of course they will have different resistances, right? They will say, for example, you put one mass in castor oil and you put one mass in air, but they will not change because of gravity. The gravitational force is blind to all this. The motion will change because the resistance, the frictional force, will change in the different medium. The gravitational force does not care about in fact, the gravitational force also will act if there's vacuum inside. It doesn't even need a medium. So
I'm just saying, let's just say you drop a ball and water. Will they fall at the same time?
Will
they reach the ground at the same time?
If you drop the same two identical shaped balls, if you drop in them.
No. I'm asking if you drop some water, if you like spill some water and drop a ball at the same time, which one will reach first?
Oh, okay. So if they're not solid, right? If that's not solid, right?
So one is not solid and the other one is solid.
So the thing is that again, that will depend on, yeah, that's a very good question. That's a very good question. But the thing is that will depend on what, how the air resistance is acting on the water drop as well. Because I don't know if you've seen these pictures of water drops in the International Space Station. They are just like balls out there. When astronauts, when they're actually trying to drink water, they just have a ball just like, so they're just balls. So they will be, as if you remove all the air, and if you remove, if there's no gravitational force, they're just going to be balls out there, right? So, but that's a good question. That's a good question. So, because that will also depend on, so if you have a mass and this whole structure of the, so what this is modeled on is that bodies are modeled as particles. Now, a blob of water, you can't really model very well as particles. So you have to worry a little bit about, the intermolecular forces and how it's held together. But so it's dropping water versus a ball is a much harder question. It's a trickier question. Why isn't the Earth a perfect sphere? Yeah. I don't know like a very good answer for that.
Ma'am, I think I know the answer.
Yeah.
So it's because of Earth is spinning really fast. The rotational speeds cause the Earth to bulge out slightly.
Yeah, so that bulge is there also. But apart from that, even the perfect sphere, it's not like a perfect smooth sphere in the same sense that, a moon, Aristotle thought moon was a perfect sphere. And Galileo showed that there are craters on the moon. So in that sense also, Earth is not a perfect sphere for various, there are mountains. But the bulge thing is true because it also has rotation. So we're not even taking into account the rotation into account. Yeah.
Viraj, you had your hand up.
Yes, I have a question. When showed in the slide about forces, it showed strong force means that a force that holds nucleus together, and weak force means force that causes radioactive decay of each other, of a nucleus. But then the name sounds so similar, but they mean like different. Why?
It's a very, very silly name. So the thing is that the strong force is easier to understand because the strong force is something that, because if you think about what is the nucleus consist of, protons and neutrons, right? So protons and neutrons of course don't have electrical charge, but if you put two protons together and you have only electromagnetic forces, what will happen? If you have two protons next to each other and you had nothing but electric forces, what would happen?
They will just repel.
They will be repelling each other, right? Right? They are like charges. So the nucleus has protons like charges together. So they cannot be held together by electromagnetic forces. So there has to be a force that overpowers the electromagnetic repulsion and holds the nucleus together. So the proton-proton forces, proton-neutron forces are strong attractive forces, but okay, gases become so that's why that's holding the nucleus together. Now, radioactive decay is a little more complicated because it's not a question of holding the nucleus together, but it's actually breaking up the nucleus and releasing other particles, and that is mediated by another force, and that's a weaker force compared to the strong force, and weak forces are a little harder to understand. They're not the same as, they're not holding the nucleus together. They're actually responsible for neutrons changing into protons and releasing neutrinos. So that's a little more complicated. But they are within all of them have only power within the range of the nucleus, which is very tiny, 10 to the minus 15 meter, and they drop to zero beyond that, like so they're not long range forces. Yeah, something about you're saying that
so
gravity
Mukund had his hand up.
Liquefying matter, is it? Whether
but before that, Mukund has had his hand up for a while. Mukund, would you like to?
Mukund, what is it? Sorry.
Like, we have different fields and forces causing different causing different forces, right? Yeah.
Right.
Example for mass, you have the Higgs field, and for electromagnetism, we have the electromagnetic field. Yeah. Now, what agent causes the gravitational field?
See, you are talking about a very, I'm talking absolutely at a classical level, like so, this analysis doesn't even know about the Higgs field. So the Higgs field comes only when you're talking about quantum mechanics. And if at that quantum mechanical level, we don't even have a quantum theory of gravity. I mean, there is no consistent quantum theory of gravity known so far. People are trying with string theory, people are trying with loop quantum gravity, various things, but there is no established loop quantum theory of gravity, just like there is for other forces. So that's like gravity stands apart there also. But
ma'am, isn't that the theory of the graviton?
Yeah, so the graviton is, if at all one talks about a mediating particle, it is something called a graviton. But, like that is an approximate version of the theory. There is no full theory of quantum gravity so far. But gravity, if you think about a mediating particle of the force of gravity, that is the graviton. Yeah.
Next, I think we can go to Akshara, and then we'll do Anish's question that's there in the chat.
Akshara?
Yes, ma'am. Does the moon's gravity cause the shape of the earth to be not a perfect sphere?
No, I don't think the moon's gravity. What the moon's gravity has an effect on is the tides. So that is a very moon's gravity has a very strong effect on the tides, the rising of water in the oceans. The shape of the earth is the not being a perfect sphere has more to do with the rotation of the earth. So which is of course like but it's not primarily due to the sun's moon's gravity. So the tides are affected by sun's gravity as well as moon's gravity, and that is a very strong effect actually, and that is something Newton studied very thoroughly, and Newton's theory can give a very comprehensive understanding of tides and predict when the tides will occur and when the high tides with what is the rise of the water, all of that. And all of that can be explained by attraction of the moon and the attraction of the sun, combination of that. Yeah.
Great. And then we had Anish's question of why do gases not become liquids due to attraction between the particles due to gravity?
Yeah. No, I think like, see, the thing is that on Earth, definitely, gravity is very, very weak. So the kind of pressures and temperatures. So how does a solid become a liquid? What is needed for a solid to become a liquid? Can you tell me? So one of the things is that you need very high pressure, temperature, all of that, right? Heat. You need also high pressures also. So the gravitational forces on Earth, there is no. I mean, they're very weak. If you so you remember that the the equation I gave, that G m1 m2 over r square, that capital G is a very, very tiny quantity. And the gravitational force can become large only if the masses are very large. And that is why in space, it's a very important force, because masses of the sun, planets, stars, galaxies are huge. And that is where gravity is dominating. On Earth, gravity is one of the, laboratories. Gravity is like a trivial force. It doesn't have large effects at all. So there's no question of liquefying using the force of gravity. It's not strong enough.
I'm not saying due to Earth's gravity. I'm saying between the particles only
Between the particles, it's even worse. Because the particle masses are very tiny, right? How much force will that produce? That's what I'm saying. To produce a considerable force, you need at least large masses, because it's G times m1, m2 over r squared, right? And now that G is very, very tiny, very, very tiny. So overwhelm that G, capital G, the constant, the masses, to get a considerable amount of gravitational force, you have to make the masses very large. That's the only way so the masses on Earth, see, that's why, like you and I are not rushing towards each other because of our gravitational forces, like it's very, very weak. But in principle, there is a small acceleration on me due to you, and you due to me. It's there, but it's very, very tiny. So all of these forces on Earth, even for very huge particles, like it's not like small particles, but even huge terrestrial size objects, gravitational forces are negligible.
But the sun is very big, so the sun should be liquid by now or solid, because it's very weak. It has very much gravity.
No, but sun gravity actually the sun large part of it is gaseous. So but that is a very different. It doesn't liquefy because of gravitational forces, and that has to be of self. If you're talking about that will be the self-gravitational force. Self-gravitational force is not large for the sun. So the stability of the sun is held by, there is self-gravitation pushing the sun inwards, but that is balanced by, that's why the sun is stable. The nuclear reactions going inside the sun give an outward pressure, and that makes a star stable. So that's why it's not collapsing. So the pressure is not there to liquefy the sun. In any case, the sun, a large part of it is gaseous. The solar atmosphere, even inside the Earth, a large part of it is liquid. No? We are only living on the crust.
Yeah. So I think Anisha's question makes sense in terms of, like, when you think of cosmic scale, the Earth exists because gravity between all the particles caused it to coalesce together, or the sun exists because, so on those scales, like nebulae exist, all of those things exist due to gravity, if my understanding of it is right. So Kanya would be able to tell better.
Yeah, so the thing is that on that scale, so gravitational forces become important when the masses are very large. Otherwise, on terrestrial scales, they are it's a very weak force. Yeah.
Yeah. Great. So I think we're already 10 minutes over time. So Vian and Shriram, if you could quickly tell your questions, then we'll just answer those and then close up the session.
So ma'am, can you describe the properties of a neutrino?
Why do you want to know the properties of a neutrino? Neutrino, see, the neutrino is till now it used to be believed that it's a completely massless particle, but now it's been discovered that it has a very small mass, but and it has a spin which is and it participates in neutrino is a particle that participates in weak interactions. So it's a neutrino.
So does it have any specified charge?
No, neutrino is chargeless. It's chargeless, almost massless. So understanding what massless particles are it takes a little doing, but it's almost massless with a very tiny mass, but it's chargeless. You know, it's very hard to detect. It's very hard to detect. It has energy, it has large energies. It also has a spin. It's classified as a particle that is called that are called leptons. And
okay, ma'am. But ma'am, do you have any courses on quantum mechanics I can attend?
No, not so far. And quantum mechanics requires, you know, like a lot of background in first understanding classical language. Which grade are you in?
9.
Ninth, okay. No, right now I'm not giving a quantum mechanics class because quantum mechanics requires a fair amount of understanding. Quantum mechanics requires a fair amount of mathematical background and some background also in classical mechanics. So right now at school level, I'm not offering a quantum mechanics course. I'm teaching a quantum mechanics course at the undergraduate level, but so far no. So far no. Yeah.
Okay, ma'am. Thank you.
So you're very interested in quantum mechanics, is it?
Yeah, I'm very interested. I'm actually in 7th grade, but I'm reading the 9th graders' books on the quantum.
Oh, you're in 7th grade, but you're reading 9th. Yeah, I meet a lot of students here now who are very interested in quantum mechanics and have picked up stuff from the books. What books are you reading?
There's a book called A Big Fat Notebook of Chemistry. So I learn about dipoles, LDFs, VSEPR theory.
Okay. Excellent. No,
Nice.
right now I'm not doing that. Maybe sometime in the future I'll think about it. Yeah.
Thank you, ma'am.
Sriram, your question?
Yes, sir.
Your hand is up. Do you have a question?
Yes, sir. I want to know the percentage
Sorry, we're
of
just asking Sriram. Yeah, go ahead, Sriram.
I want to know the percentage of gravity in the moon, ma'am, and I also want to know whether the percentage of gravity in the moon is the same everywhere, ma'am.
Everywhere means all
around the moon, ma'am.
See, the thing is that percentage of gravity is a little odd question to ask. But if you think about the gravitational acceleration, something that, see, for example, here we have around the Earth, we have more or less a uniform gravitational field with all objects are falling with 9.8 meter per second square, right? So near the moon, near the Earth. Similarly, on the around the moon, it's just that it's about 1/6 of this, and it's more or less uniform. It's more or less uniform. Now here, similar to this, so in that sense, there is some. It's roughly 1/6 of the gravitational force here. Yeah. So the acceleration, but it's uniform. It's uniform for all practical purposes. Just like it's 9.8 meter per second square here, there it's just 9.8 by 6 or whatever, like some factor of it's just so that's that. But that's one thing to realize, that what we're talking about, all this thing that I've been telling you about, they're falling together in a uniform gravitational field. It's confined to a small region, relatively small region. So if I cannot do the experiment by dropping a feather on the moon and dropping a feather on the Earth, bowling ball on the Earth and expecting them to reach the surface at the same time. No, because the acceleration due to your gravitational fields are constant near the moon, near the Earth, but they are different values. So you have to do it in a small region of space. Yeah.
Okay, ma'am. Thank you.
Okay.
Somebody had a question about Usain Bolt, which I probably don't know how to answer, but.
Okay. Arahan, any last quick question? We should really be wrapping up.
Yes.
Yes, go ahead.
I have a question. I have heard about a particle which is called a God particle. It is heard that it has negative charges. Can you explain me a bit about that? Because I think it might be related to gravity.
Which particle?
The God particle. They call it. I don't know the name.
God particle is quite different. It's called it's actually a very unfortunate name, but it's actually called the Higgs particle or the Higgs boson, and does not have negative charge. It has no charge at all. It's a chargeless particle, and it had been found a few years back at CERN after a long search. And it's a very interesting particle because within a certain theory, it is a particle which is responsible for giving mass to all the other known particles that we have. And to understand how that works, unfortunately, one has to know a lot of, have a bit of a background and know a lot of the mathematics. It doesn't have negative charge. It has no charge at all. It's an uncharged particle.
Okay.
And what they call a zero spin particle, and it's called a Higgs particle. After the person who one of the people who proposed it, and it's been somehow called the God particle, and that name has stuck. Yeah.
Okay. Well, thank you all so much for attending today's session. It's been a lot of fun. We will send an email later with the link to the recording. You can also just subscribe to our YouTube channel. I've shared the link in the chat. That way you'll get notified of any new recordings. And then, Sukanya, did you have something to say?
No, I just said that if you now think about it later and have any other questions, you can send them by email or something like that, and I can try to answer.
Yes, you can respond to our email with any questions, and I will share them with Sukanya. And I hope to see a good number of you in the course starting next week, exactly a week from now. Thank you all. You can
Thank you all.
feel free to
Thank you,
unmute
Soren,
and say
ma'am.
bye.
Bye, thank you.
Thank you, Soren, ma'am.
Thank you.
Bye.
Thank you, ma'am.
Thank you, sir.
Bye-bye.